Welcome back to Gabversity, where facts don't care about your feelings. And now, this evening here at 10 p.m., 13th of September, that's a Wednesday. Oh, you know what that means? Captain Deltron, it means that Friday the 13th is coming up in October. I was born on Friday the 13th, by the way, just so everyone knows. Probably why my life has so much bad luck. L. Brooks, lovely to see you. So we're going to talk about main sequence stars first. Now the thing about main sequence stars, just like any stars, it is impossible to go inside the star and see what's in there. So there's ways to do that, which is building mathematical models. Every star is balanced between two forces. There is always the force of gravity pushing it in, and the internal pressure of the fission or fusion, whichever one it is, that's trying to push it outwards, and so it remains balanced at a certain place. But of course, you know that logic dictates that as soon as that fuel runs out, gravity is going to just win. Gravity waits, but you know, gravity's patient. Okay, the internal structure of a star can be described by four simple laws of physics, two of which you have already encountered. The laws of hydrostatic equilibrium describes the balance between weight and pressure. And the law of energy transport describes how energy flows from hot to cool regions by radiation, convection, or conduction. Okay, so radiation, I think everyone knows where heat radiates. Convection and conduction. Now, we're going to talk about those as we progress in this lecture. To these two laws, you can add two basic laws of human nature. The conservation of mass law, which says that the total mass of the star must equal the sum of the masses in its shells, with the added requirement that the mass be smoothly distributed through the star. No gaps are allowed. The conservation of energy law says that the amount of energy flowing out of the top of a shell, Ernie Banks, in the star must be equal to the amount of energy coming, stop moving around on me touchscreen, amount of energy coming in at the bottom of the shell plus whatever energy is generated within the shell. This means that the energy leaving the surface of the star, its luminosity, must equal the sum of the energy generated in all of the shells inside the stars. Good morning, Mr. Ernie Banks. This is like saying that the total number of new cars driving out of a factory must equal to sum of cars manufactured on all the assembly lines inside. That's actually, you would think, James Joseph, you would think that that's a simple concept. But there you go. Hey, welcome back, my friend. Always a pleasure to see. Banter is fun. Back for more banter. The four laws: energy in a star cannot vanish without a trace or appear out of nowhere. All right, so that's a fair assumption to make. The four laws of stellar structure, described in general terms, can be written as mathematical equations. By solving these equations numerically using computer programs, astronomers can build a mathematical model of the inside of a star. I love that stuff because they're actually rebuilding with mathematics the blueprint of what's inside the star that we can't see and that we could never see. If you want to calculate an accurate model of a star's interior, you have to divide the star's volume into at least 100 concentric shells, and then write down the four equations of stellar structure for each of the shells. So that's 400 equations per star, and there's 100 billion of them in one galaxy, and there's 100 billion in each galaxy, and there's 100 billion galaxies. Whew, that's a lot of math equations. You should then have 400 equations that would have a total of 400 unknowns, namely the temperature, density, mass, and energy flow in each shell. When you solve those 400 equations simultaneously, and that is done via a matrix, we've done some matrix algebra before, okay, it's not easy, but the first such solutions were calculated by hand. They were done by hand before a computer, a 400 matrix. That is insane. I'm getting really tired. Oh no, I'm not going to be able to finish all of my lectures today. Oh, I'm pretty disappointed. You know how long they took to do those equations per star? They took months and months of equations to solve a 400 simultaneous equation with 400 unknowns. Oh my goodness. Who would do that by hand, man? That is just crazy. Now computers instead of by hand when it took months, right? So like, like imagine, now, and then thank you very much, True Faith. By Christmas, they would solve the equation. A computer now takes a few seconds. So that goes to show you that when computers become artificially intelligently aware, right, they can do in a few seconds what takes a smart human, a few months. Man, we are doomed. We are so doomed. Such a table is a stellar model. The table shown shows a model of the sun containing only 10 layers. But it's extracted from a model that has many more layers. The bottom line in the table represents the center of the sun, and the top line represents the surface. I'm so sorry. I think I'm going to have to stop this lecture early and go to sleep. I think I've had it. Oh my god. So over 1 month I took, this is 10%. You want me to show you 10% of the equation? I don't think you want to see it. I don't think you want to see this equation. 10%. Oh my goodness. Alright, I'm going to show it to you. Let's do it. There it is, my friends. So here is the table of 10%. Hold on, that was only 10 equations. Sorry, not 10%. 2.5%. Why they serve ants. Ernie Banks, that is so true, and you've said it so brilliantly. You do that. You know, I think Slim Grady did that in the last scope, and you've done that over and over. Just like what a woman would dream of. Sorry, that's a very bad joke, but Ernie Banks, why would they serve ants? That is so true. Why would they serve ants? That is exactly the truth. Man, does that not scare the living hell out of anybody at all? And we're just sitting back. I don't know. I just see this coming. It's just crazy. All right. So that's not light through the curtain. It's reflecting off the ceiling. Yes. No, it's black night at the moment. Ernie Banks. Yeah. It's your memes are great, but in this case it's scary because it's so freaking true. The mass inside each shell. You know what? I'm gonna tweet that out right now and quote you. Excuse me. I'm about to tweet out what Ernie Banks just said. Right. What do you call it? Artificial intelligence. Quote. Why are we serving ants? Ernie Banks from the Gab Smacked think tank. Why are we serving ants? Love it. All right, that's tweeted, my friends. All right, let's go back to what we were reading. What is hydrostatic equilibrium? It is the weight on each layer that is balanced by the pressure in that layer. That is called hydrostatic equilibrium. That means the pressure that's pushing outwards is balanced by the gravity which is trying to compress the star. Okay. That's pretty cool, actually, if you think about it. Imagine if you could squeeze something together and then it just starts emitting nuclear radiation. It's just crazy. Hopefully all thinks like Peter. AI thinks like Peter. Yeah, imagine that. Wouldn't that be lovely? Look at that. There you go. You've already got one like, Ernie Banks. Why are we serving ants? That's too good. Stellar models let astronomers understand the inside of a star, and they can then follow the evolution of the star step by step as it ages over billions of years. Modeling stellar structure. You got to admit, that is amazing. We as ants, who live for the less than the blink of the eye of the star, are able to, during that blink, figure out the whole star's birth, death, its age, how it works, when they appeared, when they're going to die, how they're going to die. I love that stuff. Modeling stellar structure and stellar evolution are highly challenging problems involving nuclear and atomic physics. We're going to do that, by the way, in quantum mechanics soon. Next week. Looking forward to it. My interview with Simon, Just Simon, that's going to be a good one. That's coming up next week, by the way. So it'll probably be on either Gab Smacked or iRational. Probably iRational. There's an iRational t-shirt still outstanding. There's one in stock if anyone wants it. $19, including postage. Xander, hello. Modeling stellar structure and stellar evolution are highly challenging problems. It's like me trying to understand God. Too good. That is too good. Modeling stellar structure and stellar evolution are highly challenging problems involving nuclear and atomic physics. Hey, you too, Xander. It's a pleasure to have you back to our think tank. Only since the 1950s have computers made the rapid calculation of stellar models possible. Heaps of us were alive in the 1950s, right? So, and my parents and grandparents were like freaking, in the 1950s. They had to calculate the structure of a star by hand, and it would take them up to 6 months to do it. Our grandparents, for the love of Christ. This is insane. All right, and many of the advances in astronomy since then have been heavily influenced by the use of these computer models. That is just phenomenal. That blows me away, that stuff. All right, let's load the next page. I think after this page I'm going to stop. Okay, so scientific models are only as good as the assumptions that go into them. Yes, my friends, just like climate change. You know, what I don't understand is why I still own my old slide ruler. That is so awesome. Man, that stuff's like should be in a museum. You should periscope that stuff, seriously. You've always got some good things happening. All right, handprint. Let's do it. Why is there a main sequence? All right, the main sequence star. Gravity pulls all of the atoms in a star inward, and that weight is balanced by the outward pressure of the hot gas inside the star. Okay. The first nuclear fuel to fuse is deuterium, the heavy isotope of hydrogen. But deuterium is rare and produces little energy. Stellar models show that deuterium fusion has little effect on a contracting star. Okay, fair enough. Hydrogen fusion is the big powerhouse, my friends. That is the... What's the name of that one? The Hindenburg. The Hindenburg. All right, so where are we? Hydrogen fusion is the big powerhouse, and when it begins, it produces enough energy to stop the star's contraction. So as soon as hydrogen ignites, it just puts the brakes on the star contracting. Gravity, see? Gravity wants to cause a problem. Hydrogen counterreacts. Gravity caused the ignition of the hydrogen. Just like the pro-Stalinist maniac totalitarianist created the rise of Trump, whether we like it or not. That one there, interesting fact. Hydrogen fusion is the big powerhouse. The main sequence is the location in the HR diagram for stars in equilibrium. Fusing hydrogen into helium. This is a related question about the main sequence that you can resolve by thinking about stellar models. Why does the luminosity of a main sequence star depend on its mass? Okay. Along the main sequence. In other words, the least massive stars are at the bottom of the main sequence, and the most massive stars are at the top. So brightness and mass are directly related when it comes to stars for some reason. And that would probably be because the rate of compression increases because of gravity. I bet you it's because of gravity. The larger, then there's more gravity, which means you need a lot more fuel to burn to counteract the force of the gravity, which means it's going to burn more brightly, which means it's not going to last as long. Stellar models can tell you why there must be a main sequence mass luminosity relation. I reckon that's what it is. Artificial intelligence, AI newsletter liked your tweet. How funny. Ernie Banks, your tweet just got liked by the artificial intelligence newspaper. What are you doing, man? This is crazy. You have a gift, my friend. You and Slim Grady have a gift. Deuterium is the hint that our sun is a second generation. Interesting. I did not know that. Thank you, Captain Deltron. You see, this is why the Gabversity think tank is awesome. I feel like together we could actually have a proper university. The keys to understanding the mass-luminosity relation are the law of hydrostatic equilibrium, which we just said. The pressure must balance the weight. We said that. And the pressure-temperature thermostat, which regulates energy production. It makes perfect sense. You have seen that a star's internal pressure stays high because the generation of the thermonuclear energy keeps its interior hot. Massive stars have more weight pressing down. We just said this. The temperature at the center of a 15 solar mass star is 34 million Kelvin. 34 million. more than twice the central temperature of the sun. The nuclear fuel at the center of a 15 molar star fuses over 3,000 times more rapidly than the fuel at the center of the sun. It's like the Hemi. The Hemi burns fuel 15,000 more times than a regular car. The American bloody beast. The rapid reactions produce more energy which flows outward towards the cooler surface, heating each level as it goes up to support the weight. When the energy reaches the surface, it radiates into space and makes the star highly luminous. Alright, the explanation for the main sequence is elegant in its simplicity, but you can go beyond that to discover more about the inner workings of stars. Interesting stuff. I think we're going to stop there because I'm a bit exhausted. And we can continue. Next lecture will be the upper end of the main sequence. Pressurized gas out of torch. More pressure equals intensity. Yeah, absolutely. I think it's basically exactly that. It's simple and yet it's amazing at the same time. Turns out there's an upper limit on the mass of stars. But we will talk about that next lecture because I'm just exhausted. I'm going to go to sleep for a few hours and then get up and then do some other stuff. Alright guys, well that was a lot of fun. Uni is much more fun when we're together. I love it. Gabversity, where facts really honestly don't care about our feelings. They really don't. They don't even know our feelings are there. Alright, love you all.